Welcome back to the third lecture on water isotopes and climate. We have learned so far that d18O variations in water, ice, and also of calcite and speleotherms can tell us something about past temperature, atmospheric circulation and rainfall changes. But we don't know yet what processes are responsible for the variations of rainfall on timescales of months, years, millennia or longer. This lecture gives us some basic information that will help us in the interpretation of paleoclimate data. About 40% of South Korea's total rainfall falls in summertime during the Changma season from late June to August. Changma is part of the larger East Asian summer monsoon system, which brings moist air from the tropical regions to Eastern Asia. Typically, summer rainfall peaks twice, in late June and late August. During the Changma rainy season, we observe a large drop of d18O of rainwater to values between -8 and -9 per mil. Why is that? We have already talked about the amount effect before. In some region of the world, including East Asia, we find the following. The more rain falls, the more depleted the oxygen isotope composition of the rain. This explains in part why there are low values in summertime. In fact, you will be able to see this effect in the rain that you will be sampling in June to August with the monthly rainwater samplers that we provided for the KWIN project. One phenomenon that brings a lot of rain and strongly depleted d18O water to South Korea are tropical cyclones, which occur preferentially in late summer, in July and in October. What are tropical cyclones? This movie shows the northwestern Pacific, including South Korea and Japan. We see wind speed in blue and red shading and rainfall in white. Tropical cyclones are massive storm systems with wind speeds exceeding 63 kilometers per hour. In the movie, they appear as large flying circular donuts, red donuts, sometimes with a hole in the middle, the so-called eye of the storm. They can reach wind speeds of up to 300 kilometers per hour. This is, you would be sticking your head out of a running KTX train. Even though the high winds can be very destructive, the largest economic damage is usually due to the flooding. Tropical cyclones are being formed over warm oceans. There, water evaporates, and through the condensation of water vapor, the atmosphere is heated and air is rising over these areas, while it is sinking over others. Due to the effect of the Coriolis force, the motion will eventually attain a horizontal spinning component. Winds will increase further, which leads to more extraction of heat from the ocean. This again enhances the up-down and the spinning motion of the air, thereby intensifying the circulation. If this process is not interrupted by other atmospheric phenomena, a tropical cyclone can be formed. Tropical cyclone season over South Korea lasts from July to October, and this is the time when strongly depleted d18O water can seep into the soils and drip into our caves. The number of tropical cyclones making landfall in South Korea changes every year. This is in part due to the fact that the atmosphere has a lot of randomly occurring changes. You probably heard about the butterfly effect. In principle, a flap of a tiny little butterfly wing could cause a tornado somewhere else on our planet. In addition to this random atmospheric noise, There is one other factor that can affect the number of tropical cyclones in the Western Pacific, and this is El Nino. El Nino is a massive warming of the eastern equatorial Pacific, which occurs every 2 to 10 years. It changes weather patterns worldwide, and it turns out that it can also increase the number of tropical cyclones near Japan and south of Korea. This could enhance further rainfall over the Korean peninsula, in particular in late summer. This figure shows rainfall in Korea since 2017. But the individual rainfall events look quite random. And this randomness, or scientists refer to it more as chaos, is very typical for atmospheric motion, and it is an essential part that we need to consider when we study climate. In addition to this figure also shows some years are wetter than others. Whether this is due to the randomness of the atmosphere or whether it is determined by large-scale climate features such as the El Nino phenomenon is an important question for scientists to address. It turns out that the influence of El Nino on the climate over Korea is relatively weak, and that the atmospheric noise is the largest contributor to the year-to-year variability of rainfall over Korea. Let's come back to the mean seasonal cycle of rainfall. Clearly, this is related to the seasonally varying distribution of solar radiation on our planet. We can now ask the question, has the seasonal cycle of solar radiation always remained the same? The answer is no. To understand this, we need to embark on a little journey to outer space. Let's suppose we fly away from our planet. If we spend a few 100,000 years outside Earth's orbit in our spaceship and observed our planet, we could see three interesting phenomena. The axis of our planet is not stable. The angle between the Earth's orbit and the Earth axis is changing by about 3 degrees every 40,000 years. This changes the seasonality on our planet, in particular in polar regions. The second observation we would make in our spaceship is that the Earth axis wobbles like a gyro, with a timescale of about 21,000 years. Right now, for instance, our northern hemisphere occurs when the Earth is farthest away from the Sun 10,500 years ago. Northern hemisphere summer occurred when the Earth was closest to the Sun. This means right now we have colder northern summers and warmer northern winters as compared to the situation 10,500 years ago. Moreover, our imaginary spaceship astronauts could also see that the orbit around the Sun changes over time. Sometimes it looks more like a perfect circle, sometimes it's much more an ellipse. These conditions vary about every 100,000 years. Why is this important? These three cycles, which we call obliquity, precession, and eccentricity, change the seasonal distribution of solar radiation on our planet. In turn, they will impact Earth's temperature, the atmospheric circulation, and rainfall patterns. The combined effect of changes in Earth's axis and orbit is so powerful that it can create ice ages. We already learned in our second lecture that as massive ice sheets are building up over North America and Europe, global sea level drops down by about 120 meters. Just as a reminder, the low sea level 20,000 years ago connected China with Korean peninsula. Instead of the West Sea, there was land. This would have clearly affected climate conditions over Korea. In fact, a land bridge would have made them cooler. Moreover, from the tiny air bubbles trapped in Antarctic ice cores, we know that the atmospheric CO2 concentration was significantly lower during glacial times. Lower atmospheric CO2 would have also caused lower global mean temperatures. But how can we know how the climate has changed in the past? One possibility is to reconstruct past climate with ice cores or from stalagmites. Another possibility is to use climate models. Climate models are complicated equations that describe the movement of air in the atmosphere and water in the ocean, the distribution of energy in water, the formation of clouds and processes on land and in ecosystems. These equations are so complex that only the fastest computers on our planet can solve them. A climate computer model is a collection of about 1 million lines of computer code that scientists developed over tens of years. To simulate past, present and future climate, our center has bought one of Korea's fastest computers, Meet Aleph. Aleph was delivered to the IBS Headquarters Center in Daejeon in November 2018. And in this little video you can see how the machine, which can do about 1.5 quintillion calculations per second, gets delivered. The overall supercomputer has 3 parts. The main computer, an enormous disk system that can store the large amounts of computer data generated by our simulations, and a tape archive that provides long-term storage of our simulations. Our center uses Aleph to simulate how Earth's climate has changed over the past 1 million years and how it will change in future in response to increasing greenhouse gas emissions and anthropogenic emissions. Let's check out some of the results. We conducted a computer model simulation that covers the climate of the last 4 glacial cycles, essentially over the last 400,000 years. The computer data show that temperatures over Korea may have been 5 to 6 degrees cooler 20,000 years ago during the last glacial maximum as compared to today. Let's bring this information back to our caves. We know that typically the temperature inside a cave is close to the annual mean temperature outside. If you go to one of these wonderful caves in Gangwon area in summertime, it can be 35 degrees outside, but inside the cave it is about 13 to 15 degrees Celsius. Quite pleasant year-round. We have learned that already that temperature plays a role in the oxygen isotope fractionation when cave water drips transform into calcium carbonate by outgassing CO2. Using this kinetic equilibrium equation, which we derived before, and assuming for a moment that the d18O of the drip water has not changed, we can see that a 5 degrees Celsius temperature change from glacial to interglacial would lead to a 1.2 per mil change of oxygen isotope values in calcite. This is in fact a lot and could be measured easily with the equipment in our lab. Moreover, we also remember that the global ocean during glacial times was enriched in d18O by about 1 per mil due to the lower sea level. This means that by adding up these 2 effects, the glacial calcite inside the Korean cave should have been 2.2 per mil heavier than calcite that is forming right now. Is this really true? Didn't we forget something? Oh yes, the rainfall. Let's continue our little calculation by including the simulated precipitation. Interestingly, our computer model shows 30% more rain over Korea during glacial periods. This must be related to large-scale reorganizations of the atmospheric circulation. Whether this is true needs to be tested using real paleoclimate data from Korean caves. After all, this is just a computer model which only knows the astronomical forcing and the physical equations of the climate system. If the present day d18O rainfall amount effect worked over Korea also in the past, a 20 centimeter change in annual mean rainfall would translate to a minus 1.7 per mil reduction in d18O. Let's summarize here. The sea level difference glacial minus present day is plus 1 per mil in d18O. The temperature effect inside the cave is plus 1.2 per mil, and the rainfall effect would be minus 1.7 per mil. What we are still missing here is an understanding of how rainfall d18O turns into drip water d18O inside the cave. In order to better understand this, we need to remember that both rainfall and d18O of rainfall have a strong seasonal cycle. They vary together, or we say they co-vary. Let's now imagine a cave in South Korea that has an average present day monthly mean rainfall of 8 millimeters per day in summertime, corresponding to a d18O of rainfall of minus 9 per mil and a winter rainfall of 1 per mil with a d18O of minus 6 per mil. The water that then percolates through the epikarst can take about months to years to reach the cave. It is then clear that the drip water d18O will be more representative of the summer rain because there is simply more water from this season. So instead of a year average of minus 7.6 per mil of rainfall, we would see a drip water d18O of minus 8.1, much closer to the summer value. Drip water d18O is therefore seasonally weighted. d18O in rainy seasons will dominate the d18O of cave drip water. If now, under some conditions in the past, the rainfall in summer was reduced, and assume that the d18O of rainfall was not changed, then it is clear that the drip water d18O will be heavier, less depleted, and closer to the annual mean of rainwater. We can see now how a change in rainfall can lead to a d18O drip water change, even though the d18O of the initial rain stays the same. Changes in the seasonal covariability of rain and d18O can cause drip water d18O changes, which will also be reflected in the d18O eventually of calcite of our speleothem samples. We can also play this game the other way around. Let's assume for some hypothetical reason the d18O of rain has changed from the present day seasonal cycle to a different one. Even if the seasonal cycle of rainfall itself did not change, the d18O of drip water in the cave would change. In our example, it will reduce, because the covariability between rainfall and d18O is smaller. Less strongly depleted d18O of rain in summertime will lead to an overall increase in d18O of drip water. In reality, we have the combined effect that both the seasonal cycle of rainfall and d18O will change over time. The story is, however, a bit more complicated because when rainfall hits the ground, it slowly seeps into the soil. The upper soil layers can evaporate some of the water, which, as we learned before from the disequilibrium fractionation of d18O, would enrich the d18O of the soil water. This evaporation itself depends on how much water there is already in the topsoil, the humidity of the air, winds and the air temperature and other climatic conditions. Let's summarize our findings. What we have learned so far is that the d18O of calcite, which we can measure in our lab with an isotope ratio mass spectrometer, we will discuss this in the next lecture, depends primarily on the cave temperature and on the d18O of drip water. To better understand the drip water under present day conditions, we visit the caves and take regular water samples. The d18O of drip water is a function of the seasonal cycle of rainfall and d18O of the rain. For present day conditions, we will use our K-WIN water samplers and a water isotope analyzer to determine how rainfall and isotopes correlate over different areas in South Korea. The next step is then to understand how these local conditions depend on the large-scale atmospheric circulation. For this purpose, we use our supercomputer Aleph and other existing observational and paleoclimate datasets. In our next lecture, we will learn a little bit more about how all of these measurements are made, and we will look at some real data from last year's Kevin project. And we will also look at Korean caves. I hope you enjoyed our little tour from stalagmites to global climate today, and I will see you next time.